So in the last video we ended up here in the conservation of mechanical energy, and we saw that the mechanical energy, if we have no dissipative forces, it's constant, and the potential energy transforms into kinetic energy and vice versa, but the sum of both is always the same, is constant. This was the last thing we saw, and now we're going to change to something different, that is waves. So that's we saw it that energy can be exchanged through waves, and when we saw a bit of electromagnetic waves and so on, radiant energy, but we're going to see it in more detail. So energy may also be exchanged through waves. And what is a wave? A wave is the propagation of a disturbance. Okay, like that. It's a disturbance, una perturbación that propagates. And this disturbance is generated at a point in space, and that is the emitting source where it is generated. And this wave transports energy but not matter, so only energy. And you're going to see a wave, an example of a wave here. So this is the wave, see? And this is the disturbance. You see it's a change in the rope. That's what we call a disturbance, una perturbación. But the matter is the same, because the matter, this part of the rope is here all the time, and this part is here. So the matter is not going, you're not throwing the rope, you're just making it move. And is this thing, this disturbance, that we call a wave. Okay, this thing. But the matter, I insist, is not like throwing a ball, that the ball is here in the beginning and goes here. The rope is staying in the same position, so the beginning is here all the time and the end is here all the time. It's just changing the shape, and this change is the wave. Okay, so let's see some properties of these waves. We have the amplitude A, that's the symbol of it. This is the maximum distance between points oscillating relative to their equilibrium. So the equilibrium would be the rope when it's not moving. And when we have the wave, this maximum point, this distance here from the equilibrium point to the maximum of the disturbance, this distance is called amplitude. And of course it's a distance, so the international unit is meters. Then we have the wavelength. This is the distance between the distance of the wave. We say between two crests, that is if we have one wave and another one here, so the distance between two waves, or two throats, and this is like the lowest point, so these two lowest points, that's the wavelength, so the distance of the wave. That's why we call it wavelength. And because it's a distance, we measure it in meters. Period. This is the time it takes a wave to travel its own wavelength. So we saw this was the wavelength distance, and I just put it here, and we're going to see how long it takes the wave to go from here to here. So I put it play. So 1, 2, 2 seconds, for example, in this wave. So the period here is 2 seconds, because it takes the wave 2 seconds to move from the beginning of the wavelength to the end of the wavelength. This, I didn't put the units because I don't know if it's 1 meter, or depending on the hand, or half a meter, or 10 centimeters, I don't know. So anyway, but it's a distance, and the time it takes to make this distance, that is the wavelength, the distance of the wavelength, that's the period. Then we have the frequency, that is the number of wavelengths that the wave travels in 1 second. This is a bit difficult to understand, but you will see it in third of ISO, in fourth of ISO, and so on. But it's the opposite to the period here. So it's not how many seconds it takes a wave to travel, but how many waves in 1 second. And the unit is hertz. That is the same as 1 over second. So it's a bit strange, but yeah. So imagine we count like 1 second, and it's like 1, and we see how many waves moved. In this case, it would be half a wave moved in 1 second, but nonetheless, that's the concept of frequency, and you're not going to have to calculate it in second of ISO. So what we have is that the greater the amplitude, so if this is higher, if you have a bigger amplitude, or the greater the frequency, or more waves per second, the more energy it carries. So we can see here that here we have in 1 second, because they are smaller, we are going to have more waves per second. So it means that this part of the waves is more energetic, and of course it is, because as we saw, this part of the electromagnetic waves are the most dangerous ones, because they are the most energetic ones. The gamma rays, the X-rays, the ultraviolet lights, and here radio waves are not dangerous at all. Here you can see longitud de onda, that's the wavelength, and this is the units in meters. So this is 1000 meters wave. So radio waves are really, really high, because it's like the wavelength is 1 kilometer, and the frequency is lower than in the gamma rays. And so we say the frequency, when it's very high, very great, very big, it's more dangerous. So just don't bother about radio waves, because they are not dangerous, but do worry about X-rays and gamma rays and ultraviolet lights. So we can classify waves in several ways. So the first criterion, it's according to the direction of vibration and propagation. We have 2 ways. For example, transverse waves, it's when their vibrations are perpendicular to the propagation. And it means that, as you can see here, it vibrates up and down, but it's moving to right. So the direction of movement, the direction of propagation, is perpendicular to the direction of the wave, that is up and down. So this is perpendicular to that. But we also have longitudinal waves, and in here the their vibrations are parallel to the propagations. Here you can see that it's compressing. So this is the wave. You can see that this is the wave that is moving, and it's moving and compressing in the same direction as the propagation. It's compressing to the right and it's moving to the right. So this is a longitudinal wave, and this is a transverse, because it's perpendicular wave. This is one classification. Another one is according to the propagation medium, and here we have again 2 types. We have the mechanical waves, and for these we must have a medium, we must have matter, and that's sound, for example. Here you can see these are the atoms, and the wave is making the atoms vibrate, and that's why it propagates. Sound is like this. So sound, what sound does is making the atoms vibrate, and of whatever it is, air, a wall, whatever, your ear. And so sound is a mechanical wave, because it needs matter to vibrate and get propagated. But electromagnetic waves, like light or X-rays or radio waves, they don't need a medium. They can propagate in a medium. So light can propagate in water. That's why you see things inside a swimming pool. Even if you're in water, you can see stuff, and that's because light can propagate in water. But they can also propagate in vacuum. They can propagate in space. That's why we get the energy from the sun, because the light from the sun can propagate even if we don't have anything in between. So again, according to the medium, we have mechanical waves. This needs matter as a medium. And electromagnetic waves, they don't need anything. They can propagate in matter, but they can also not propagate in matter. They can propagate in the vacuum too. But let's talk a bit about the sound. So the sound, oh, this is, you cannot really see it. Why is this here? So this one shouldn't be here. Okay, sound is the propagation of vibration objects through a medium. It is a mechanical wave and it cannot propagate in vacuum because, again, sound is the propagation of vibration objects. So when we have here the sound, for example, as you can see, if we strike a drum, what happens is that we are these atoms here are getting closer of the air, and this is going to transport, like we saw here. Okay, they are going to compress and they are going to move it to the next atoms and so on and so on, and that's how you get the sound to some point, because it's hitting the atoms. And when this vibration gets to your ear, it makes your eardrum vibrate, because it's the same. An eardrum is, el tímpano is just like a drum, and that's you receive it here, and that's it goes to your brain, and that's how you perceive sound. So because it vibrates, if you don't have a medium, you don't hear it. And that's why in space, even you see that in Star Wars movies, you see all the spaceships doing and when they fire, you hear the sounds too. Not true, because sound needs a medium, and in space there's no matter, so nothing, you can hear anything in space. But let's see some properties of sound. So the intensity first, that's what we call volume, and this is it's related to the energy. Remember, the energy was the amplitude, so if we have this wave, the greater the amplitude, the louder it is, so the most intensity, more intensity. And so this is an intense sound, and this is a quieter sound because it has less energy, because it has less amplitude. And the unit is decibels, as you know, because maybe you have heard that when there's a problem, or washing machines, they sell that it's 49 decibels, and that's like really quiet for a washing machine. Anyhow, another property, pitch. This is related to the frequency of the sound wave, and is how many, remember, frequency is how many waves you get in 1 second. So here, because they are smaller, you get more waves in 1 second, and here you get less. And that's the difference with high sounds, so los agudos y los graves. Okay, that's the amount of waves you get per second, and the unit, of course, because its frequency is in hertz. Low frequencies sound low and deep, and high frequencies sound high and sharp. And finally, timbre. That's the quality, and that's the difference when we, for example, use different instruments to make the same notes. We can hear there's a difference, and that's because what changes is the shape of the wave. So this object does the perfect wave, but every instrument does a similar thing, but not quite the same. And these small differences are the ones that help you to distinguish if you're hearing a flute, or you're hearing a violin, or you're hearing a trumpet, or it's because of these differences in shape. Because as you can see, the maximum is the same, so the amplitude is the same, the wavelength, the distance here is the same, so the difference really is the shape of the wave. And finally, we're going to talk about echo and reverb. Uh, so because the human ear can distinguish sounds separated by 0.1 second, but the sound has a velocity, has a speed. If, for example, we talk and the sound goes to a wall and comes back, if we do the calculations and taking into account that the sound speed is the speed of sound is 340 meters per second, and we do the calculations, we need at least 17 meters so that the sound goes and comes back, and we can distinguish the sound that we throw and the sound that comes back. If it's, again, farther away than 17 meters, we're going to hear our sound back, and that is the echo, because we can distinguish the one that goes and the one that comes back because it's farther away enough. But if the distance is less, we're going to have some mixed waves, because then it would get to us in less than 0.1 seconds, and then we won't hear the perfect and the clean sound, and we will hear something like mixed, and that's what we call the reverb. And just to talk about noise again, this is noise pollution, and this is the excess of annoying sounds, most probably caused by human activities, because normally nature sounds are not annoying. And the problem is that noise pollution can cause physiological harm and psychological harm. And here you have some examples of 0 decibels is really like nothing at all. And normal breathing is 10 decibels, and a quiet conversation 20 decibels, normal conversation 40, a loud one is 60, the train going by is 100, nightclub 110, an airplane taking off is 120, and here is the pain threshold. More than this, it hurts. And in a rock concert, you can feel like after it, you cannot hear the same. It's because it's over this threshold. And an explosion is 180, and that really causes a lot of harm in your ears and everything, of course. And well, this is the homework for this unit, because this is the end of the unit. And well, so that was it.